So I'm Bradley Kuszmaul. I did this work with Matteo, Frigo, and Justin, Mazzola, Paluska, and Sasha, Sandler, who's here. And there were a whole bunch of other people involved with this. So these are just the four people who sort of were the first people on this particular project and what's a big project at Oracle is the Oracle Cloud Infrastructure. I'm going to talk about file service. And so what is file storage service? Basically, the game is that Oracle's operating a cloud, and so you can think of something like Amazon Web Services that's Amazon's cloud. Oracle also operates a cloud, and we're smaller, but we try. So the game is that we set up a file system for you, and that file system shows up as an IP address in your virtual cloud network, and behind that IP address is a network file server. And we run the network file server, and as you write data into it, we make sure that there's enough storage, and you don't have to manage the server. You also the business plan is also maybe you're renting NFS clients from us, and maybe you're running a bunch of other software that we can make money on, and because Oracle's all about making money, right? You pay for what you use, so there's some price per gigabyte month, and you start at 0 and grow to be as big as you want. We have a whole lot of file systems that are less than a megabyte, and we have a bunch of them that are more than a petabyte. So there's a big dynamic range in file system size. So we designed, so here's the architecture. And basically the picture here is the green things, the NFS clients, those would be your server that you were renting by the hour. They talk to a presentation host, and the presentation host speaks NFS. This is architected so that maybe in the future we could do other protocols besides NFS, like the Windows protocol. The presentation host is running a whole bunch of NFS processes that are actually doing the communication, and they talk to your various clients, and those clients belong to different customers in general, so those IP addresses actually only make sense in the context of a network namespace. On the back end, sort of to the right, are a bunch of storage hosts, and these storage hosts have a bunch of disk drives in them. Well, hard drives, no, NVMe, that's what they are. So a whole bunch of storage, and they run two services. One is DASD, which is sort of IBM lingo for what a disk drive is, direct access storage device, and I'll talk a little bit about that. Dendron actually implements the file service. So DASD is sort of a distributed block device, and Dendron is the file service. And mostly I'm going to spend time sort of buried down in the DASD part. I'm not going to talk very much about the NFS process, or really very much about Dendron. Now, if you were building a system to solve this problem, to file service, you could imagine a simpler ideas like, oh, let's just go get a bunch of file servers, and we can put NFS, we can put file systems on them and put NFS servers on them and pack a bunch of, if the file systems are little, so the server's kind of the blue box, the file systems are the reddish circles, and you can have a little file system like /A and a medium-sized file system like /D, and you pack them in there, and as the file systems grow, you have to figure out how you're going to migrate file systems around. And eventually you get some big file system like the petabyte file systems that I mentioned that don't fit on a single server, and somehow you have to get those distributed across several storage servers. So what's wrong with this sort of simpler idea? Because this is simpler architecture than what we actually did. So one of the problems is failover and replication. This is supposed to be enterprise-grade file service. So if a machine crashes, we have to keep serving data. You have to figure out how you're going to do the migration of these little file systems around and load balance it, and how do you handle the big file systems, and how do and so we couldn't figure out how to use this simple architecture, so we ended up doing the more complicated thing. And the more complicated thing boils down to figuring out how to build a distributed data structure that crosses servers. So here's, I just made up this. This isn't a particular data structure. I've got the servers are still blue, and the data structure nodes are reddish, and these dark these purple nodes, these purple edges are pointers within the data structure. So maybe you have a little doubly linked list over here and a child of some node and so forth, and I want to maintain some invariance on that kind of a data structure. So the game is we're going to figure out how to solve this problem and then build a file system on top of it. Well, let me do a digression about exactly what data structure we want. What we want in principle is inodes, because that's how you implement POSIX file systems. So an inode has, this is review possibly for a lot of you, but let me just sort of go through it anyway. Each file or directory or other file system object is represented by a numbered node. So here I've got 4 inodes, inode 0, inode 90, and inode number 42. And they have permission bits in them. So the first one is the directory. You can tell because it's drwx. I don't know if you can see that. The second one's also a directory, and the third one is a file. It doesn't have a D. And this is the little piece of the file system that's representing a file named /u/foo.txt. So the directory here, this is the root directory. It's inode number 0 by convention. And it has a little directory here that maps u to an inode. And then this is that directory, and it has a directory that maps foo to this inode. And then this inode, which is a regular file, has a block map in it that maps offsets to block identifiers. The data is stored in the blocks. So that's what inodes are, and that's, in principle, what we want to implement. And you could imagine going ahead and directly implementing this data structure as the distributed data structure, and some vendors, I think that's actually what they do. But we did not. We said, well, we want to abstract this a little bit and make it easier or harder or something. So instead of implementing the inodes directly, we think of these inodes as tabular data, and we code up the inodes as data. So this is the same little directory structure, and it's represented by 3 tables. There's an inode table, and all these tables are like key value tables. So there's the left column, which is a key. The right column is the data. So the inode table has inode number 0 and some information. Inode number 42 and inode number 90. So those are the inodes. And then below that, I've shown the directory table, which basically, the keys are pairs, which are inode numbers and file names. So if at inode number 0, u that maps to inode number 90. At inode number 90, foo.txt maps to 42. And there's a block table that tells us for each inode and for each offset what the block is. So that's how we represent inodes as tabular data. Now it's key value data, so we stick them into a search tree. And so the thing that we spent a lot of time on, this is the distributed data structure that we spent effort on making correct, is to make a distributed B-tree. And a B-tree is just a search tree. It's got a wide fan out so that you can exploit the fact that IOs are expensive. And in this B tree, all the data is stored at the leaves, so technically it's a B plus tree, but I think it's kind of pointless to talk about all the distinctions between B plus and B star and all those trees. They all have the same asymptotic performance, so we just use the one that everyone uses, which is B plus trees. This one also has a doubly linked list among all the leaves, so you can traverse the leaves from left to right if you want to as well. So that is the sort of a quick picture of the B tree that we implemented. And these purple pointers could generally cross from one machine to another. There's only one B tree. All the file systems are stored in that B tree. So some file systems are little, and they just use fewer key value pairs, and some file systems are big and use a lot of key value pairs. Even the small systems end up spread across multiple servers. Well, updating a B tree requires atomic operations across servers. So here's a little example of a typical B tree operation. I want to split this. I've got this B tree. It's got this node here, which is a little bit too full, and I want to split it to even it out. So what I want to do is I want to allocate a new node, which is sitting here in the free list. And I want to put some of the data from here into here, and I got to update all the pointers. So here's the new free list. It skips that. The doubly linked list connecting everything together is there. I've had to update the parent. And The way I want to get this implemented is I want all those changes to be done atomically. I don't want to be in a situation where if something fails in the middle that I've taken something out of the free list and dropped it on the floor, or I've got it in the free list and it's in the Btree, or any of those kinds of failures. Don't want to have that happen. So the rest of this talk is basically about how we went about solving the problem of implementing this kind of atomic operation. Whoop. Well, the classic solution is to use two-phase commit. And basically, the game with two-phase commit is you have a bunch of participants who are the different servers, and they want to do some transaction. Each participant records enough information that they can roll the transaction forward or backward, and they get ready to go. And then there's a designated coordinator that decides to commit the transaction. The coordinator notifies everybody whether to go forward or backwards, and that's what happens. And if one of the participants misses that notification, they have to ask later what happened so that they know whether to roll forward or backward. So that's two-phase commit, and it's kind of the way you make a distributed data structure. The problem with two-phase commit is what happens if the coordinator is running, you get everything ready to go, and you're about to commit, and the coordinator crashes. Maybe the coordinator doesn't come back because it's had a hard drive failure or something. Or maybe the crash happened before the commit, or maybe the crash happened after the commit. At any time, the coordinator could come back, so you can't kind of decide without asking the coordinator what happened. So the clients don't know what's going on, and they get stuck for as long as it takes for the coordinator to come back, which could be forever. Well, the solution to this problem is Paxos. Paxos doesn't get stuck. I'm not going to explain it in a lot of detail, but Paxos lets you come to a consensus on a single value. Multi-Paxos lets you make a log. Once you've got a log, you can make a state machine because you basically have some state memory and you just apply log entries to it. Think of the log as commands that happen on the state, like insert something into a tree, maybe. Paxos handles the cases where messages get lost or duplicated or machines crash and come back. And as long as you have a majority of the machines eventually coming back, the system keeps making progress. So file service uses Paxos to implement two-phase commit. And so each participant in the two-phase commit is a replicated state machine. And it solves the problem that two-phase commit has, is if the coordinator dies and doesn't come back, you get stuck. Well, the coordinator doesn't die because it's a replicated nonstop state machine. Each of these replicated participants we call an extent. So how big is an extent? Well, an extent has to fit into a single server, so it can't be, you can't like make one extent that holds everything because this Paxos state machine has to fit in one server. There's a lot of overhead for the state machine because this is implementing two-phase commit. So we don't want the extent to be too small. We don't want to have a whole extent for every node in the Btree. That would be too much overhead. So we size the extent so that several hundreds of them fit on a server. So maybe it's a gigabyte or maybe 100 gigabytes of space or something like that. The extent state machine is a few megabytes. So there's this interesting distinction in the way we've implemented this. Is there's the state machine and then there's the gigabytes of pages that the state machine manages. These extents are small enough that we can move them around for load balancing or to exploit parallelism when a machine crashes and we have to make a new replica. We don't have to, we can spread out the work of re-replicating the data to make failure recovery faster. And we use five-way replication for these extents. So we programmed, so now I'm going to sort of switch to sort of the programming model of how we implement this. Once we've got this two-phase commit implemented, what's the abstraction that I get to use as the Btree implementer or as the user on top of the Btree to program it? And it's a kind of an optimistic concurrency style way of programming. We have an operation that we call Multipage Store Conditional. It's very similar to some of the processor primitives like load link store conditional, except it operates on several pages at a time. So the game is you get to read up to 15 pages, and you want to read fewer because fewer, smaller transactions are less likely to conflict or have other problems. But you could read up to 15 pages, and for each page that you read, you get a version tag, which tells you how many times the page has been modified. You compute new values for the pages, and then you present the new values along with those version tags to the MPSC operation. And either it writes them all atomically, and that can only happen if the pages haven't been modified, or if anything goes wrong, it doesn't write anything. So this is, so you say, well, let me try to change the Btree in this way, and you try, and either the transaction succeeds or it fails, and maybe you try again. These operations are linearizable, which means that they can be viewed as having occurred in a total order, and that total order is consistent with the real time that the transaction happened in. It's a limited transaction, so it's not too big because it's only 15 pages, which means we can statically allocate all the buffers and everything. We don't have to deal with the problems that databases have to deal with, where you maybe have a transaction on many gigabytes of data. We don't get to do that. But it's not too small. It would be hard to make a Btree if I could only modify 1 or 2 pages at a time. I need to be able to modify several pages at a time, at least if I want to have it to be easy to program. And there's no locks at this level and above. If you acquire a lock and you crash, the system would get stuck because you've got this lock. So the way we program here is you don't acquire the lock. You read some data, you try to write the new data out, and if you crash anywhere along the way, well, your transaction aborts or it succeeds. Either way, it's okay. So I'll talk briefly about performance. There's a simple throughput model, which is if each server is bringing a network interface, it's got so many gigabits per second of network bandwidth. When we write data, we have to write it 5 times into 5 places. So the simple model is that you take the performance of all the network interfaces in your fleet, and you divide by 5, and that you cannot exceed that speed for write performance. That's the thou shalt not exceed this speed. Queuing theory says you really can't run at 100%. So queuing theory might suggest you could run at 70% without having the latency go up. We don't do that well. We manage to run at about 1/3 of peak and have the system do well. So the simple model is that you take the bandwidth divided by 15, because there's a factor of 5 for the write bandwidth and a factor of 3 for sort of queuing theory overhead. And that's the total bandwidth that the fleet can offer to customers. And surprisingly, this very simple programming model just seems to work for almost all workloads that are throughput oriented. And I'm not going to have time here to talk about latency. But there is this sort of interesting curve that I came up with, which is I have a bunch of NFS clients on some particular fleet. The paper's got details about it. And so the x-axis is the number of clients pushing as hard as they can writing data in. The y-axis is the bandwidth that we're getting. And there's 2 curves. One is for data where you're overwriting blocks, and the other is where you're having to allocate the blocks while you write it. So the blue one is the one where you have to allocate. And this looks like a speed-up curve for a multiprocessor system, right? Speed-up curves always have this property where things kind of speed up until you run out of parallelism or something, and then they flatten out. And so I did a curve fit, and the speed-up curve says that this fleet can write 3.3 gigabytes per second, and that black dotted line is the curve, and the curve is actually sort of the harmonic mean of the part where you get linear speed up until you run out of parallelism, and then you get limited by the fleet performance. And so I kind of like it whenever something turns out to sort of, this is like, reminds me of the days of yore when I worked in supercomputing, and you always got this curve, right? You always get this curve when you do parallel computing. And the data points just are amazingly tightly fit to that curve. So that is the Oracle Files service. We are, in fact, hiring both students and engineers. So if you're interested in working on this kind of problem, you can come talk to me. There's a lot of interesting problems in the cloud. The scale's, it's one of the few places where you get to sort of do the things that we used to worry about for high-performance computing, where we worried about hyperscalability. It's a commercially important place where that kind of hyperscalability actually matters, and there's interesting problems there. So it's kind of surprising that at a place like Oracle, you get to do this kind of research.
Thank you. So any questions?
It's going to make the trek to the microphone.
Jeff Canning, Harveywood College. I seem to recall that the number 15 was motivated by you had a transaction situation that required that number. It's not just an arbitrary number.
Yeah, so the biggest transaction I needed for one case in the Btree was 15. And it hardly ever runs, but
if you...
Matteo wanted it to be 8 or 7 or 5 or something. But
or 3, yeah. Small, right? Smaller is better.
But we only have to pay the cost in terms of transaction conflicts when we actually use the large transaction. So as long as most of them are small, we're happy.
How painful would it be if you ever discovered a situation where you needed 17?
Well, we'd have to recompile code.
Okay, so it's easy.
So this describes what you do with one Btree. At the beginning, you showed 3 tables, one for blocks assigned to files, and other inodes and other directories. So how do you do the higher level transaction to keep the file system consistent?
So we can do transactions on pages, and it turns out that, feel free to unplug that. So we do the system I described talked about transactions on pages. The Btree gives us transactions on key value pairs. Each key value pair you modify or read touches one page in the Btree.
So you're updating 3 Btrees potentially, correct?
Well, there's one Btree that those 3 tables are put into. I didn't tell you the detailed schema, but you can sort of imagine a prefix on the table that says which table number it is and then put it into one tree. Or you could even mix them a little bit differently where you have another prefix to that, which is which customer it is, so that you have a different table for each customer. So there's lots of tables, but there's only one Btree.
Okay, let's thank our speaker again.